In this video, we're going to calculate the electric field for a dipole. In another video, we've calculated the electric field around a point charge. But this time what we're going to do is we're going to have two separate charges and we're going to calculate the electric field around a dipole. It's going to be a plus and a minus charge. So let's set the situation up. Here is my little dipole. I've got a plus charge which is on top just for sake of convenience or any other reason. Plus charge on top. I've got a negative charge down the bottom. I'm going to give them each a value of charge Q, so that clearly they've got the same value of charge little q, plus, minus down the bottom. Let's give it an axis, okay? And what we're going to do is we're going to calculate the value of the charge, in fact, along this y-axis, and then I'll leave it as an exercise for you to calculate the value of the charge anywhere else in the space, or in particular along this x-axis. So, as I mentioned, we need to calculate the value along this y-axis. So we need the distance between these two charges. Let's call that little s. The distance between these two charges is little s. We're going to calculate the value of the charge, or the value of the electric field, should I say, up at this point y. And just as a little reminder, what we had calculated for the point charge is that this is the value of the electric field, okay, and this is the magnitude of the electric field around some point charge. And if you remember, this went off. This is just a bunch of constants. This was the value of the charge, and this is the distance r squared. Okay, so what we can do in a situation like this when we have a dipole is we remember that vectors such as this sum. Okay, so we can calculate the electric field up at this point y. We can calculate the contribution to the electric field from the plus charge, and we can add that to the contribution to the electric field from the minus charge. So let's formalize that a little bit. We want to calculate the total electric field. At this point, we're simply going to calculate the magnitudes in this case. So the total magnetic field is simply equal to the electric field. The total electric field is simply equal to the electric field, the magnitude of the electric field from our plus charge, okay? And I'm just going to label this with a little subscript E, plus the sum of the electric field, the value of the electric field from our minus charge, okay? So from our negative charge over there. I'm just going to swap pens because that one doesn't seem to be working all that well. So we've got the electric field from the plus the electric field from the minus. Let's first work out the value of the electric field from this positive charge. Okay, so just as a reminder, this is the point I am up here. This is my positive charge up here. I've got the equation. I'm treating this essentially like a point charge, and I'm this distance away, right, from my point charge. So I've got my value of the electric field is equal to, from the plus charge, is equal to 1 on 4 pi times epsilon naught, multiplied by the value of the charge, which in this case is simply 2, divided by r squared, the distance squared, okay? And the distance in this case is the distance along the y-axis, but that distance from y down to the x-axis takes us the whole way down into the middle of our dipole, but that's not the actual distance we want, so we want the distance y minus a half s, okay? So the distance here, r is y minus a half s, and of course, that is all squared because we've got the point charge, it falls off like 1 on r squared, the electric field falls off like 1 on r squared. So this is the value for the electric field from the positive charge. Likewise, I can write down the value of the electric field from the negative charge. This is simply 1 on 4 pi epsilon naught. This time, the value of my charge is not positive q, but it's negative q, so this introduces a minus sign up here, negative q, and this time my distance is y plus 1/2 s. And I've got to again square it. Y plus 1/2 s, because again, I've got to go the whole way from y down to the x-axis, plus another little half bit of s here, plus the half the distance of the dipole. Okay, and this is basically enough to set up my entire thing. So going through now, E tot here is just equal to the sum of these two, E plus E minus. So that's just the sum of these two. So I end up with, there's a common factor in here, 1 on 4 pi epsilon naught. Both of them have a q, so let's put my q up the top. And then I've got brackets, so I've got this one is simply 1 on y minus a half s all squared. And then here's my minus sign, 1 on y plus a half S all squared. Okay, this is a bit of an ugly expression, so let's spend just a minute simplifying this thing down. Okay, I've gone behind my writing, I apologize. So this is Q on 4 pi epsilon naught. I'm going to put everything over a common factor here, so I'm going to put it over y minus a half S squared, y plus a half S all squared, which means that this top one has to be multiplied by y plus half S. This is simple algebra. If you're not following what I'm doing, then just simply write it down yourself. I would encourage you to do this. And the reason I want to get through this is that we're going to quickly work out some of the properties of this electric field around a dipole. Okay, so now I can expand my brackets and I can cancel things out. You can see that I'm going to get a y squared term from here. I'm going to get a y squared term from here. There's a minus there, so they cancel. Okay, likewise, I've got a half S all squared, gets me a quarter S squared, minus plus half S all squared, so they cancel. So what I'm left with, in fact, is I get the cross terms, which becomes 2 times y half S, which is ys, minus minus plus, I get, let's write Q on 4 pi epsilon naught, and I just get a 2y times S divided by all of this junk, y minus a half S squared, oops, put the squared in the wrong spot, y plus 1/2 S all squared. Okay, this expression looks reasonably ugly, but I want to do one very quick thing. I want to say, what happens if I'm not at y here, but I'm actually way further up, right? So in other words, what I want to do is I want to say the distance between my two charges. So for example, if this is two molecules, a positive charge and a negative charge, or two atoms, positive charge, negative charge, what is the difference? But that distance is going to be a lot smaller than my distance away from the charge, okay? So in other words, to formalize that, what I want to say is when y is much, much bigger than S, okay? So again, just to emphasize this point, y is the distance between here and here. It's much bigger than this distance between here and here. Or in other words, I'm sitting well away from my dipole. What is the value of the electric field? So when y is much, much bigger than S, hopefully you can see that y minus a half S is approximately just equal to y, okay? So when y is much, much bigger than S, then the value of this thing is approximately just equal to y, to a very good approximation. Likewise, also y plus a half S is approximately equal to y, okay? And so I end up just writing this denominator as y minus a half S all squared just becomes y all squared. Likewise, this term, y plus a half S all squared, simply becomes y all squared. Okay, so I've got y squared times y squared, which is y to the 4. So in this limit, I've got the magnitude of E far away from my source is equal to 2. I should write approximately equal to 2 Q y S on 4 pi epsilon naught y to the 4. So this y to the 4 comes from in there. But then I've got y to the 4 on y. This is 2 QS on 4 pi epsilon naught y to the cube. And the thing that I want to emphasize now is simply that I've derived this, and this says that the electric field falls off like 1 on the distance cubed. So for a point charge, you can remember up here, we had that as I moved away from the point charge, I felt the electric field fell off like 1 on r squared, 1 on the distance squared. In this case, as I move away from a dipole, at least moving along this vertical axis, as I move away from this dipole, then the value of the electric field falls off like 1 on the distance cubed instead of 1 on the distance squared.